Okay, so let's recap from last class where we talked about the cerebellum. We talked about its role in error detection and correction through all of its connections with the visual system, vestibular system, and its influence on the cortex. It is heavily involved in balance and coordination. And remember that on the internally generated, externally generated continuum of movements, the cerebellum is heavily involved in externally generated movements, that is, visually or orally guided movements. The clinical application is that cerebellar dysfunction leads to lack of coordination, impaired balance, and more difficulty with externally generated movements or completing them successfully. So today we're going to talk about a major subcortical structure of the basal ganglia. And this is titled Energizing, Selecting, Integrating, and Driving Motor Strategies. And it all seems so automatic. And we're really going to talk about energizing and selecting today. Our overall learning goals to design and deliver. I want you to be able to design and deliver effective movement interventions for patients with basal ganglia dysfunction. And at the end of this session, you should be able to answer these three questions. What is the unique role of the basal ganglia in motor control? What is the result of basal ganglia dysfunction? Meaning, what are the signs and symptoms? What movements are most heavily impacted? And lastly, how can movement be improved in persons with basal ganglia dysfunction? So in order to answer those questions, these are the things you need to know. The basic anatomy. We're going to go over the major cortical loops, but we're going to focus today on the one skeletal motor loop. And then we're going to get a little bit more in detail of the circuitry of the basal ganglia and talk about the direct and indirect pathways. So let's start off with a video first. So this video, you'll see someone with basal ganglia dysfunction, Parkinson's disease, and we're going to be talking about that in depth later. But for now, I'm just going to pause this. I want you to just take a piece of paper and write down what you see. What is the quality of the movement? What is happening? Everything that you see. Okay. And this is just a side note for the recording that I would take. This recording is the video is 2.5 minutes long, and I would let the students watch that whole video and write down their thoughts about what they see. Okay. So let's get to the need to know. Let's review some basic basal ganglia anatomy. Basal ganglia, okay, so these are structures deep to the motor cortex, or deep to the cortex itself. It is made up of 5 nuclei, so just 5 big groups of neurons. The caudate, the putamen, the globus pallidus, the subthalamic nucleus, and the substantia nigra. Okay, these are some input structures, some output structures, and some modulating structures. The caudate and the putamen are collectively called the striatum. The globus pallidus has 2 components, the GPI, GPE. We'll talk about those in a second. The subthalamic nucleus is located somewhere else in the midbrain. I'm sorry, and the substantia nigra are located in the midbrain. So the input structures of the basal ganglia are the caudate and the putamen. But for our purposes, we're really going to focus on the putamen. That is the input structure and a critical component of the skeletal motor loop. The modulator, the substantia nigra, we'll talk about that. Substantia nigra is where dopamine is produced. And for the basal ganglia circuitry to function and work properly, you need the substantia nigra. Close that, sorry. And we'll talk about the subthalamic nucleus. That adds another level of complexity, but we'll get into that in the next session after this one. So for right now, let's concentrate on the input structures, putamen, the output structures, which is the globus pallidus, and specifically the internal part of the globus pallidus. Okay, busy slide, lots of information here. These are the major cortico-basal ganglia thalamus loops. Okay, and in all of these instances, you get the basal ganglia is getting information from areas of the cortex. Then it's being processed through the basal ganglia. Then that information goes to the thalamus, and then it goes back up to the same cortical areas that it came from. Okay. For right now, we're going to concentrate on this loop on the most left-hand side. This is the skeletal motor loop, what they call the body movement loop. Okay, that's what's of most concern to us as physical therapists. Okay, so what's happening here? Where's the information coming from? It's coming from the primary motor cortex, some from the premotor cortex, but importantly also from the supplementary cortex, motor cortex. That information from all those cortical areas is coming into the putamen. Now it's at the basal ganglia level, and here's the putamen, the input structure. It's getting processed. It will go to the globus pallidus internal segment. Okay, that's the output structure of the basal ganglia. It gets outputted to the thalamus, and then the thalamus sends this information right back up to the cortex. Okay, cortex, basal ganglia input, basal ganglia output, thalamus, back up to cortex. So why? Why is it doing that? Why are we having these big loops through the basal ganglia? Something important must be happening here. Well, if we get down a little bit into more depth, we're going to see that it, again, like the cerebellum, to understand it, you have to understand some of the circuitry. So within the skeletal motor circuit, there are direct and indirect pathways. Okay, the direct pathway basically involves the globus pallidus internus, and the indirect pathway is a little bit longer. It takes another step, and it uses the globus pallidus externus as well. So let's get into it a little bit. Okay, let's talk about the direct pathway. So let's just take a look at this upper loop here. Okay, so from here, the short loop. Okay, so we have information coming from the cortex. Remember, this is all semanotopically organized. Information coming from the cortex. It stops, it's coming into the putamen. Okay, and look at this direct pathway. From the putamen, it goes right to the globus pallidus internus, where its output goes to the thalamus, goes back up to the cortex. Okay, the fun part gets into if you look at what neurotransmitters these components are using. So the output from the putamen is inhibitory, and all the output from the GPI is inhibitory. But the output from the thalamus is excitatory. This is glutamate. So what's happening? So this input, this excitatory input, is coming in from the motor cortex, but as it leaves the putamen, this is inhibitory to the GPI. Well, if the GPI has an inhibitory effect on the thalamus, and you inhibit the GPI, you're essentially inhibiting an inhibitor. So it's a minus and a minus makes a plus. So the net effect of information going through this direct loop is that you get more excitation out of the thalamus, which means more excitation up to the motor cortex. So in fact, you are energizing, you're helping to select or reinforce that motor information that came in. You're reinforcing it, you're energizing it. Okay? If we take a look at the indirect loop, one more. If we take a look at the indirect loop, that takes an additional step. So it goes from the putamen to the GPE to the GPI, and we're going to disregard all this down here for a minute. Indirect, GPE, GPI, thalamus, and up. Okay, so it's a little bit longer, but the net effect of all that, now that we have that extra step in there, is that it actually turns on the GPI, which means the GPI is sending a lot of inhibitory input into the thalamus, which reduces the amount of information that gets back to the cortex. So the net effect is inhibitory. So this is in fact like putting on the brake. Okay, the direct pathway is energizing. It's putting on the gas. It's reinforcing what's already being sent to it from the motor cortex. But the indirect pathway is putting the brake on. Okay? Now, to add in a little bit of detail, the indirect and direct pathways both work because of dopamine. Okay, so there's two types of receptors there in the putamen. A D1 receptor, which activates the direct pathway. We just said that's the gas that facilitates movement. Okay, and there's also a D2 receptor, but it inhibits the indirect pathway. The net effect of that is to facilitate movement. So when the dopamine is working properly and you get information into the putamen from the motor cortex, supplemental motor area, the net effect when dopamine is working properly is that you get facilitation of movement. Okay? But in basal ganglia disorders, which of Parkinson's disease is probably the most common, what you know the most about, okay, the dopamine is no longer working. There's not enough dopamine. Substantia nigra is not making it. It's not around. Okay, so there's no activation of D1 and D2 receptors. So the end result is the direct path is not facilitated. So there's no putting on the gas. And the indirect path is not inhibited. That means there's a lot of brake. So there's a whole bunch of braking and no gas. And the net result of that is you get loss of movement. You get poverty of movement, and we call that hypokinetic disorder. It is the cardinal feature of Parkinson's disease, which is hypokinesia. Okay, hypo, loss of movement. So even if you just take a look think about those direct and indirect pathways, we can see that the basal ganglia has a clear role in movement selection, focusing neural activity and suppressing alternate movement patterns. It really energizes what the plan is. So let's go back to the video. And I want you to now watch it again with renewed eyes. What is this? Put some more meat onto it. Why are you seeing what you're seeing? Can you describe it using the language that we've just talked about?